Enzyme purification and specific activity. How can you apply your knowledge of biochemistry to real-world problems? Well, how about generating an environmentally friendly alternative energy? What you know about enzyme purification can actually help refine biofuel production. Imagine you are in charge of producing biofuel at an industrial scale. In hopes of finding an effective way to degrade plant biomass, you look to natural decomposers, fungi. Fungi contain an enzyme called beta-glucosidase, which is able to take partially degraded cellulose, called cellobiose, and hydrolyze it to make free glucose, which can be used for energy. Your job is to produce exactly the amount of active beta-glucosidase that you need for your reaction, because too little will mean you can't produce energy from all the cellobiose you're using, which is a waste of cellobiose and bad for the environment, and too much will mean wasted beta-glucosidase and wasted money, which is bad for business. But how do you tell how much purified active enzyme you need, and how much you have? If your enzyme isn't purified enough, you might have less active enzyme than you think. And how do you fix your purification method if it's not working well enough? Where would you even start? The best way to quantify enzyme purity is to determine its specific activity. Specific activity is calculated by dividing a measure of enzyme activity by the total protein amount in your sample mixture. So how do you get those two numbers? You can measure enzyme activity through various assays that all work basically the same way. You start with a sample of purified enzyme, so in this case, beta-glucosidase. Then you perform a reaction under specific known conditions where you give your enzyme the reactants it needs and measure the amount of product, or glucose, it produces over time. Generally, scientists have defined an enzyme unit as the amount of enzyme needed to produce 1 micromole of product in 1 minute under specific conditions. Thus, for simplicity, we often write enzymatic activity in terms of units, rather than micromoles of product per minute. Okay, so you now know what the activity of purified beta-glucosidase is, but how does that help you figure out how pure your sample of beta-glucosidase is? In other words, how do you get from beta-glucosidase activity to beta-glucosidase specific activity, which is a measure of purity? Specific activity is beta-glucosidase activity, which, hang on, what units is that measured in? Right, micromoles of glucose per minute, or enzyme units, divided by the total protein amount of your sample mixture in milligrams. This gives you a measure of how much beta-glucosidase activity there is in any given amount of your sample. Okay, so you still need the total protein amount in your sample mixture. How do you measure that? You can use a colorimetric technique like the Bradford assay and spectrophotometry to measure the concentration of total protein in your sample mixture. Do you remember how the Bradford assay works? Protein reacts with Bradford reagent to produce a colored substance, and you can use a spectrophotometer to measure the concentration of that colored substance. From the concentration in your sample's volume, you can calculate the protein amount of your sample in milligrams. But why bother calculating specific activity if you already have the protein concentration of your sample? Remember, you're trying to purify beta-glucosidase from fungi, so there are more proteins in your sample mass than just beta-glucosidase. Specific activity tells you how much beta-glucosidase activity there is in your mixture of other proteins. You will need this information to use your purified protein mixture to break down cellobiose and make energy. Specific activity also helps you monitor the success of your purification process. It's possible that some condition of your purification procedure, like buffer pH, might actually reduce beta-glucosidase activity through degradation, or you may unknowingly co-purify an inhibitor of beta-glucosidase. So, how do you use specific activity to help you purify beta-glucosidase? You're starting with crude fungal cell lysate. First, you do a salt fractionation, which uses varying concentrations of ammonium sulfate to precipitate beta-glucosidase plus other proteins. After this round of purification, you end up with a lot of the beta-glucosidase activity that you started with in your crude lysate, but also a large amount of protein other than beta-glucosidase. So your total protein concentration is high. And taken together, that means your specific activity is pretty low. What happens next if you perform ion exchange chromatography to separate proteins based on charge? In this example, you use anion exchange, where positively charged proteins flow off the column and negatively charged proteins, like beta-glucosidase, bind to the positively charged column. After you've washed off the positively charged proteins, you use an increased concentration of salt to release beta-glucosidase and other negatively charged proteins from the column and collect them. Because science is messy and not perfect, you recover less beta-glucosidase activity than you started with, due to some enzyme loss. However, you reduce the total protein amount in your sample mixture by a lot, because you eliminate many proteins with a different charge than beta-glucosidase. So, your specific activity is greater than after the first salt fractionation step. This is great because during a purification, your goal is for your specific activity to increase after each step. Finally, you use size exclusion chromatography to filter proteins in your mixture based on size. Proteins larger than the fractionation range of the column do not enter the porous beads and flow off the column first, while smaller proteins travel through the porous beads, which will take a bit of time, and so they come off later. You still lose some beta-glucosidase activity, but you reduce the total amount of protein recovered even more than the previous two steps, so your specific activity increases yet again. So, at the end of the purification process, enzyme activity relative to the total amount of protein is much greater than at the beginning, because at each step, you got rid of protein from your mixture. But you designed your purification to selectively get rid of other proteins more than beta-glucosidase. And there you have it. You have successfully purified your beta-glucosidase sample. After calculating specific activity, you now know how much beta-glucosidase activity there is in your sample. So, you can tell if you have enough active purified beta-glucosidase to hydrolyze the amount of cellobiose in your reaction. So now you're ready to take on your next challenge. Whether it's producing biofuels using purified fungal enzymes or acing your next biochemistry course, you'll know what to do with specific activity and enzyme purification.